Alright, so now we're going to be looking at the mechanics portion of this edX A-Level Maths curriculum, starting off with the Applied Book number 1, Chapter 9. So the first topic we're going to be looking at are time graphs. So we're going to be looking at displacement time graphs and velocity time graphs. So starting off with the displacement time graph. We know what displacement is, right? It's the vector form of a distance, okay? So we're going to have displacement on the y-axis and time on the x-axis, as shown by here. And as you can see, you have to get the units. So displacement meters, right, is the length, and time, the units will be seconds. So make sure you apply the units to the axes. And then we're going to have a certain graph, which I've drawn an example here, where I've labeled A to F. Now, first things first, for a displacement time graph, one characteristic that we need to be aware of is the gradient. Okay, so the gradient here is the change in the displacement over the change in time, which we know from looking at some mechanics or looking at some vector equations is the equation for velocity. So the velocity is changing displacement over time. So one of the characteristics, or the characteristic for a displacement time graph, is that the gradient is equal to the velocity of a certain particle. And so using that, we can describe the velocity of particles moving. So let's look at this one here. So I've written out these little key points, like key letters, right, A to F. So we're going to have to now describe what's happening to the velocity of the particle. So O to A. As you can see, the gradient is increasing, right? It's a positive gradient, and it's a straight line, so the gradient is also constant, meaning that the particle or the thing in motion is experiencing a constant positive velocity. So moving forwards at a constant speed, essentially. A to B, the gradient is now 0, right? Which means that actually the particle has now stopped suddenly, okay? So from A to B. B to C and C to D is just a straight line downwards, right? Once again, it's a straight line, and this time it's a negative gradient, which suggests that it's actually a constant negative velocity, which means that it's actually moving backwards in time as time goes forward. At the point C, as you can see, it crosses the x-axis, right? So this just determines that, it tells us when the displacement is 0, right? Displacement just means the distance from the starting point to a certain point. So if the displacement is 0, it just means it's reached or it's come back to its original position. D to E, once again, it's going to be a constant, well, the gradient is 0, right? Which means it's going to be stopped. And E to F is a slightly weird one. As you can see, it's also a positive gradient, right? However, it's not a straight line anymore, which suggests that the velocity is not constant anymore. So you can see here that as from E to F, the gradient is decreasing with time, which means that it is a positive velocity, but the velocity is getting slower and slower and slower as time goes forward. So this is just a description of what is happening for this particular particle in the motion. Let's look at this question here. So we have Sarah, who left home at 10 o'clock and cycled north in a straight line. The diagram shows a displacement time graph for her journey. Work at the velocity between 10 and 11. Okay, so this is a displacement time graph. So we know that the velocity is just going to be equal to the gradient, right? Because it's just the change in displacement over the change in time. Okay. Now, important things to know when we're doing mechanics is that the units, right? Because units, we always have to change it into meters and seconds. As you can see here, the units are kilometers for distance, and the time is in hours, right? So we're going to have to change that later to meters per second. Anyway, displacement from 10 to 11, as you can see, it goes from 0 to 12, so the displacement will be 12. This is 12 kilometers, I need to times this by 1,000 to get into meters. Over the time, it's 1 hour, so changing that to seconds would be 60 times 60 like this, which will give me 10 over 3 meters per second, like so. On the return journey, Sarah continues past her home before returning. Estimate the time that Sarah passes her home. When Sarah passes her home, it means that she started at home and she passes home, which means even though we don't care about the distance, the displacement will be 0, right? Because we only care about start and finish points. So therefore, to look at the graph and see where does she cross the time axis. As you can see here, she crosses it roughly at this point here, so that's roughly 12:45. C. Work out Sarah's velocity for each of the last 2 stages of the journey. So the last 2 stages would be the one where she's going down from here, and then when the one she's going up like this. So let's look at the one going down. So once again, velocity is going to change in displacement with time. So change in displacement is the final displacement minus initial, right? Final will be, you can read it off here, right? -3 minus the initial will be 12. Over time, you can see it's from 11:30 to 1, so that's going to be 90 minutes. So it's going to be 90 times 60. And then it just changed to hours, right? Times it by 100. And as you can see, this will get 1,000, sorry, this will give us a value of -25 over 6 meters per second. Okay. And the second last part will be when she goes back up again, right? So same thing, velocity is changing displacement. So final displacement will be 0 minus initial, which was -3. Times that by 1,000 to get into meters. and then we divide it by the time. It's from 1 to 2, so that's just 60 minutes, so 60 times 60, and we should get a value of 5/6 meters per second. As you can see here, you get a negative positive, which makes sense, right? Because this negative version just means that it's moving backwards, which is shown by the negative gradient. This positive one just means it's moving back forwards again, and it's shown by the positive gradient of the graph. D, calculate Sarah's average speed for her entire journey. Now, right, this is the average speed. And remember, velocity is the vector form of speed, right? So speed is just the magnitude, okay? So what we need to do is speed is just equal to the total distance divided by the total time. So we don't really care about moving forwards, backwards, it's the total distance. So you can see here, the total distance will be the sum of going 12 forwards, okay? And then this distance here, she's not traveling during that distance here, so we don't have to include that part here. So it's just 12 plus this distance here, and then this distance here, okay? So it's the sum of all these distances. That's gonna be 12 plus, what do we have here? 12 to minus 3 is 15, plus 3 again. So that's gonna be total distance multiplied by 1,000 to change it into meters. Over the total time, okay? So the total time, she started off at 10, she finished off at 1 o'clock. So that's a time of 3 hours. So 3 times 60 times 60. This will give us a value of 25/12 meters per second, okay? So you have to know the difference between speed and velocity. Velocity is the vector form of speed, and speed just means just the magnitude, okay? Right, so that's the displacement time graph. We're now going to be looking at the velocity time graph. And so on the y-axis now we have velocity rather than displacement. That's why it's called the velocity time graph. And so you make sure first things first we put the units. So velocity, the units will be meters per second. Time, still units will be seconds. Now for a velocity time graph, there's two features, unlike the displacement one, which is one feature, right? So for the first feature, it's going to be the gradient once again. For a velocity time graph, the gradient is actually going to be equal to the acceleration of the particle, okay? Because acceleration is the change in velocity over change in time, and change in velocity is the y-axis over the change in time in x-axis, which is the gradient. Now the second feature for a velocity time graph is actually the total distance traveled by the particle, and this can be worked out by the area under the graph. Okay, this is an important characteristic. So the total distance will be worked out by this total area here under the graph. Okay, so for a velocity time graph, there's actually two features that we can actually work out from this kind of graph. Right, let's go by explaining some of these features again. So O to A, as you can see here, it's increasing straight line positive gradient, which means that it is accelerating. The particle is accelerating. Right, A to B, the gradient is 0, right? But that means that it's no longer accelerating, which means that it's moving at a constant velocity. B to C is a negative gradient, which means it's decelerating, meaning the opposite of acceleration, right? And C to D, once again, is going back up with a positive gradient, so that's also going to be an acceleration. Okay, so that's how we describe each part of this journey. Okay, let's try this question here. So a train starts from station X and moves with constant velocity acceleration 0.6 meters per second for 20 seconds. The velocity it has reached after 20 seconds is then maintained for t seconds. The train then decelerates from this velocity in a further 40 seconds, stopping at the station Y. Sketch a velocity time graph. So first things first, we need to sketch the graph. So on the x-axis, we're going to have time, like this, units seconds. On the y-axis, we're going to have velocity, units meters per second. So let's break this out into each individual step. So the first step, it says it's accelerating at 0.6 meters per second for 20 seconds. So for 20 seconds, it's accelerating, which means it's a constant gradient, straight line up, okay? And then we should work out at what point it stops the velocity, it stops accelerating, right? So we know that the acceleration is the change in the gradient, or change in velocity of change in time. So we can say as 0.6 is equal to velocity over time, which is 20, so velocity is going to be 12 meters per second. So it's going to accelerate up to a velocity of 12 meters per second. Next part of the journey. The velocity as reached after 20 seconds is then maintained for t seconds. So this 12 is then maintained for a further t seconds, okay? So this gap here is now going to be t. So this time interval will now be 20 plus t like this. Okay? You have to make sure you label each point very carefully. And finally, he then decelerates for a further 40 seconds, stopping at station Y. So it's going to start from 12, stop at Y, right? So it's going to reach 0 again. So it's going to be 40 seconds worth. So it's going to look something like this. Now this time here will be an extra 40 seconds added onto 20 plus t, so it's going to be 60 plus t here like this. So this will be the velocity time graph for this certain example. Given that the distance between the station is 4.2 kilometers, find the value of t. So now we're given the distance, right, 4.2, which means we know for velocity time graph, the distance traveled is actually just the area under the graph. So this is just 4.2 kilometers, changing into meters always, so 4,200 meters. So now I can just find the area under the graph and equate it to 4,200. It's a trapezium, right? So I can use the trapezium equation. So it's going to be this length here, which is t plus the bottom length, which is 60 plus t, over 2 times the height. In this case, height will be 12 like this. That way I can work out what t is going to be, and t, if you work this out, should be equal to 320 seconds. Right, C, the distance traveled by a train while it is moving with a constant velocity. So a constant velocity is when it's traveling at 12, right? So that's going to be when it's going from this here to this here. So the distance we're going to look for is that just the area under this section of the graph, okay? So that section is just a rectangle, so it's going to be height 12 times the distance, or the length, which is t, which we worked out from earlier, 320, which would give us a distance of 3,840 meters like this. Let's just try one final one. So a motorcyclist M leaves a road junction at time t is 0. She accelerates from rest at a rate of 3 meters per second for 8 seconds, and then maintains the velocity she has reached. A car leaves the same road at time t is 0. The car accelerates from rest to 30 meters per second in 20 seconds, and then maintains the velocity of 30 meters per second. On the diagram, sketch a velocity time graph. Okay, so we're going to have to draw two graphs on the same graph. So once again, we're going to have velocity, meters per second, and then time, seconds. So let's deal with each one separately. So let's go for the motorcyclist first. So she accelerates from rest at a rate of 3 meters per second for 8 seconds. So it's going to be a straight line upwards, like this, until 8 seconds. So we need to work out at what velocity she stops accelerating at. We know acceleration is change in velocity over time. So 3 is equal to change in velocity over 8, so therefore velocity, or change in velocity, is going to be 24. If it started off at 0, this will now be 24 meters per second. And she maintains this velocity consistently afterwards like this. So it's going to look like this for the motorcyclist. Let's label it M. Right, the second one, the car accelerates from rest to 30 meters per second in 20 seconds. So if 20 is here, she reaches 30 meters per second, like so. So this is now 30, and then she maintains that speed consistently afterwards. So let's label that C. So this will be the two velocity time graphs for each individual motorcyclist and the car. Right. Find the distance of the pedestrian from the road junction. So they both pass the pedestrian, right? So let's say this is equal to this. Let's say this point is where they pass it at this value of t. Okay. So what we can equate, or we need to do some equating, right? If they both pass it, it means that because they started off the same position, it means they must have traveled the same distance. So what we can do is now equate the two distances together. And the way we work out the distance traveled, or just the area under each graph, right? So let's look at the motorcyclist first. Once again, the area on the graph, let's split up into a triangle or rectangle. So this is now going to be 24 times 8 over 2 for the triangle, plus this rectangle distance. Now this distance here, if that time is t, then the length will just be t minus 8 times the height, which is 24. And this is equal to the distance under the blue line, or the car's line, right? So let's split up again, triangle, like this. So that's going to be 20 times 30 over 2, plus the distance. Now this time here, this length is going to be t minus 20 times the height, which is 30, like so. And so what we can do is that I equated the two distances together, right? Because they are the same distance. And so therefore, if I work out t, I should get a value of 34 seconds. They wanted distance, right? The distance of the pedestrian. So what I can do is plug t into either equation, right? Because they should get the same answer. And the distance traveled will be 720 meters, like this. Okay. So as long as you know what the features of a displacement time graph and a velocity time graphs are, then you can work out or create further equations to solve these kinds of problems.